Hi everyone, welcome to today's video. If you have ever worked with Linux binaries, you have probably come across the term ELF. But what exactly is the ELF file format and why is it so crucial in Linux-based system? We'll break it down today with real-life examples. Towards your right, you can see the screen. So this is a beautiful picture from this book called Practical Binary Analysis, and we'll be referencing this book today to understand different parts of the ELF binary. And towards your left, you can see this hello.c program, which is not much. You just have a header inclusion followed by you are printing the hello world. Today, we'll use this hello.c, and I have already compiled this C file to a hello ELF file format. You can check with this file utility and you'll see, okay, this is a 64-bit ELF LSB position independent executable. This is the binary we have, the ELF file, and towards your right, you see different portions of this binary. And today we'll try to understand what are the different portions and how we can actually link this hello executable to the different sections of the um, ELF file format. So what is the ELF format? So the ELF file format is the standard binary format for executables, object files, shared libraries, as well as core dumps in Linux-based system. It is the structure that helps the operating system understand how to load and run your binaries. You can see the ELF file diagram. So think of it like a well-organized container with 4 key sections. The executable header, you can see the executable header first. Then you have program header, and then you have multiple sections, and then you have section header corresponding to each sections. So ELF file format, basically 4 different sections: header, program header, sections, and section headers. Now we'll go one by one to each component of it. First, I would like to start with the executable header. Every ELF file start with the executable header. This is like the table of contents of the binary. It tells the OS, hey, I'm an ELF file. Here's my architecture. Here's my entry point, and here's where you can find my program and section headers, etc. So if you look very closely, this is the executable header. And executable header basically have multiple elements in its header structure, which is nothing but this ELF64EH header structure. Within the structure, you always have this first few characters, which are called magic bytes. Then it store information like type information, like is it relocatable, is it executable, is it dynamic information. Then you have few more information like what kind of machine architecture it is using, is it x86 64. Then you have a few more entries like what is the entry address of your program, and there are plenty. We'll try to see one at a time. So to do that, you can run this utility called readelf, and you provide this option -h, and then you just give the name of your binary. So this is how the ELF header of our hello program looks like. Maybe I should zoom it out a bit. Yeah. So you can see these are the first few bytes, which are called magic bytes, and every byte has some certain format. For example, it start with this hex 7f. You can see the 7f here. Then this thing, if you convert it to string, you'll see it's ELF, and there are other data, right? Class, version, etc., etc. Then you can also see, let's see the type information. So this E-type information is directly related to the type here. It is saying that it's a dynamically linked position independent executable file. You can see other information like what is our entry point address, which is stored in E entry. Then you can see what is the start of the program header, what is the start of the section header, like this. This is start of the PH offset, that is your program header, and then the next is section header, etc., etc. And there are other information like size of them, extra flags, etc., etc. Right. Now we'll skip the program headers for now. We'll move to section and section headers, but still, what are the difference? The major difference we'll try to highlight here. So at the static linking time, the ELF5 is viewed as a collection of sections, each holding code, data, or metadata, or any important information. However, at the runtime, the OS sees segments instead, which grouped section based on permission as well as alignment for loading into memory, etc., etc. So this is the common difference between program header and the section header. Section and section header is basically used at the viewing at the linking time, but once the linking has been done, the loader sees this chunks of sections in terms of program header. Now, again, coming back to the sections, so you can see it contains multiple sections, and there are many sections, but these are the few important sections. So for example, this interrupt section is for dynamic linker path, and then you have the init section for code to run before main, and then you have program linkage table for function stubs in the dynamic linking, and the most important one is the text, which is basically your main code. Then you have fini, which is basically for cleanup code, and these three basically are part of global memory. RO data basically stores the constants, variables you define in your program. And for example, in our hello world, this hello world is basically a read-only data, right? So it will go into our RO data. Then you have data, basically, which has like initialized data. So for example, if you have an initialized array in your global definition, then it will go to data. But if you have an uninitialized array allocation, that will go to BSS data. And at the end, you have this section string tab. So basically, it will note down all the names of the sections and etc., etc. Um, yeah, so you can have a look at what kind of sections you have. But before that, you can see for the section header, similar to executable header, you have this particular structure which contains like multiple information. For example, section name, then what is the type of the section, like is it writable, allocatable, or executing instruction. And it also had like multiple flags. For example, is it a program bits, or is it a symbol table information, or is it a string table information, is it relocatable, does it need dynamic symboling, etc., etc. Right. So you can have a look at your sections basically by doing readelf, then sections, and then you just type your program. So this is all the sections you actually have in your hello program. Let me zoom it out a bit. Yes. So you can see the interrupt section, then you can also see init section, PLT section. There is this plt.got, which is related to global offset table, and it has something to do with the lazy binding we discussed in the previous video. We'll have a separate video there, but it is for dynamically linking the library function into your main code or into your actual binary code. And there is, you can see BSS, symbolic table, etc., etc. You can see also the type information. So for example, text.text section is program bits, and you can also see the flag information, which is A and X. X means it is executable. And then you can also see the other information like offset information, like starting from the start of the binary, what is the offset of this particular section, etc. And then, yeah, So you can see that this informations are also related here. So readelf dash dash sections hello basically give you a combination of these section headers. And then if you really want to have a look at each section, you can go to the address mentioned here in the section header. And if you go to this particular offset address in your binary, then you will see, okay, actually from here, the sections are starting. You can actually do that using object dump function. So for example, let's look at this text section, which is supposed to be start at 1168, and you can use object dump minus d for the disassemble, and then you give your binary name. You will see hello here. And let's go to the start of this particular section. See, this is where it is actually starting the text section. So basically section header contains all the address, and using that pointer or address, you go to the actual sections. Yes, now the last one are the program headers. As I said, program headers give the operating system instruction on how to load the binary into memory. They define loadable segments like the text segments for code and the data segments for the variable. Each program header specifies some kind of information like they did for the section header. So this is the structure of the program header. It contains multiple information like what is the type of this program header. Is it dynamic, interpretable, or you need to load it? Then flags, it is readable, writable, or executable. What is the virtual address? What is the physical address? What is the file size? What is the size when it is in memory? And then alignment, etc., etc. Now let's look in the hello program, how does it actually look like? To do so, you can again use your readelf utility, and you have to write readelf dash dash wide dash dash segments, segments, and then you give your file name. So you can see there are multiple sections. So each of this is basically one section. You can see this particular load section, and then this is the offset, this is the virtual address of it, then the physical address, then the file size, and how will it look like in the memory. And then this is R is for like read permission, and then alignment with respect to offset. Okay, so what are program headers? So basically there is no separate section, like separate block like we have in the sections which actually contain the data. Program headers are combination of the sections basically. And why do you need that? Because during the loading time, we need to do some kind of optimization to make sure we are actually loading in optimized blocks, or we cannot load section by section because we have more capacity than that. So this is how program headers give the picture of the binary to the loader. So loader knows which one to load now, which one to load later, and how to actually optimize it. And how do you know which basically program header element correspond to which sections? And that you can see using this section to segment mapping. So for example, here also you have multiple sections. For example, the first section is only mapping this inter, and then second section is basically mapping all of this section. Then init plot, then plot got is actually getting loaded in the third segment. So for example, this is our first one, right? And you can see this is like interp, and you can also see interp here. And let's try to look at, okay, yeah, so now you have init, finit, the particular thing, and so on, right? You wanted to look at the text section. So this is basically the text section, the init section, etc., where your code actually getting started via the init function. So it is one of these loadable program headers, right? So yeah, so basically this demonstrates how sections are grouped into segments for execution, clarifying the difference between linking time sections and runtime program view. So again, in a nutshell, to summarize, the ELF format is the backbone of Linux binary, organizing your code, data, and execution flow. Stay tuned for the next video where we'll dive into lazy binding as well as dynamic linker. And don't forget to like, share, and subscribe for more deep dives into binary analysis. Thank you.